So now, in the last section, we talked a lot about how to identify code in R that was running slowly and why it was running slowly and what to do about it within R, and like how to change our R code to be faster or avoid these common problems with copying objects and slowness in R. And now we're going to talk a little bit about if those methods fail and our R code is still just slow, either because our data set's too big or we're just trying to do a lot of iterations over something. Basically, what happens when R is still just not quite good enough and we need to push R a little bit harder to get more performance out of it when our data sets are too big or things like that. So what can we do to scale our analyses in R up to larger data sets, more iterations out of a Bayesian method or whatever we're doing? So we're going to talk about scalability in R. So first we're going to talk about how to scale CPU performance in R. So we're going to talk a little bit about parallelization in R, how to run things in parallel. How to scale memory performance in R. So if you have a really big data set that you can't actually load into R, or a big data set that you can load into R, but you can't actually do anything with it once you've loaded into R because everything breaks if you actually try to run LM on it or something. We'll talk about how to handle large data sets like that in R. And finally, we're going to finish up with if R itself is still just not quite good enough and you want to get your hands dirty with some C or C++, how to write some C or C++ and call that code from R. So we'll look at the Here Be Dragons versions of that, and I'll also show you RCPP that JJ was talking about earlier. So you'll get to see it all. We're probably going to be moving through this a little bit fast, but all of the examples are online. So let's start with scaling CPU performance in R. So lots of times you want to improve your performance while still writing your code in R. You're not ready to dive into C or C++ yet. Parallelization is often an easy way to do this, especially if you have some kind of method that is embarrassingly parallel. So what are examples of some of those problems? So for example, you're trying to fit many statistical models at once. So you have an experiment and you have a bunch of different proteins and you want to fit the same kind of model to all of those proteins. You could send the subsets of the data set for each individual protein to different machines and run all of those models at once. Or you're fitting some kind of Bayesian model running multiple MC chains, then this is another example where you could run all of those chains in parallel and concatenate the results together to get a better estimate. Or bootstrapping, so this is when you're resampling from your data set to get a bootstrap confidence interval or some kind of bootstrap estimate for a parameter. And another example is cross-validation. So you're running the same model on the same data set, but leaving out different parts of the data set. Cross-validation, that's really important when you're doing some kind of classification. You want to do cross-validation, and cross-validation is another example of a method that's relatively easy to parallelize. So within R, there are a couple of different approaches to writing code that can run it in parallel. I'm going to be talking about two primary packages that you can use to write parallel code in R. The first one is the parallel package, which is typically included with any regular R installation. So you should already have the package parallel if you just downloaded R from CRAN. And another package called for each, which can be a little bit more useful if you want to write the same code and include that if you want to write some code that can be included in a package and leave it up to your users to decide whether they want to run that code in parallel or not, and leave it up to your users to decide whether or not they want to register a parallel backend that code that you wrote can then be written in parallel. So with parallel, you have to write a little bit different code because you're calling parallel versions of functions, so you adjust the way you write code a little bit. With for each, you can write the same kind of code and execute it either sequentially or in parallel. So first, let's talk about the parallel package. So The parallel package is actually an integration of two older packages that had existed on CRAN for some time and were finally integrated together into the parallel package and became part of the core R packages. So now they're included with all R installations. So it integrates two packages called multicore and snow. So multicore was a package primarily for parallelization on the same machine, primarily in Mac and Linux. So multicore didn't work on Windows, and it implemented parallelism by using Unix forks. So what that means is you have an R process that you're working on, and in Unix operating systems like Mac or Linux, you can fork that process. So it basically just create duplicates of that process, and that's how multicore worked. The Snow package had several. Snow stood for or stands for Simple Network of Workstations, and so Snow works by this in a similar way to multicore. It relies on creating additional R sessions, but rather than forking them, it creates new R sessions, and then it's up to you as the user to send data to those different R sessions and manage them a little bit on your own. So both of these packages have been integrated into the newer Parallel package, which is what I'll show you today. So let's start off by loading the Parallel package. So in the Parallel package, there's this function called detect cores. So I'm just going to call that, and we see that the number of cores on this computer happens to be 4. And so that's useful just for if you want to set a reasonable default whenever you're creating a cluster. Just calling detect cores on your machine is a straightforward way to set up a reasonable default for the number of additional R processes you want to create. So let's go ahead and set up our data set, and we're going to fit linear models for a bunch of different proteins, like I was suggesting earlier. So we'll go ahead and create a data set and filter it so it just contains all of the light channel, since that's what we actually want to do the analysis on. So first, we're just going to create a simple function that fits a linear model for a single protein. So in this case, we're writing the function, and it takes in a data set. We're going to assume that data set is some subset that only includes the data for a single protein, and then fits a linear model to it. So then we're going to group the data by protein with this nested data frame that Seung-Hang talked about earlier. So now, so fit DIA is this nested data frame with a row for each protein, and this list column where each element of this list column is a subset of the data that corresponds to just that protein. So I did this to make it easier to just send these subsets of the data to different parts of a cluster later on. But first, we're just going to try running it sequentially using MLApply and see how that works. So here, I'm just going to time how long it takes to fit a linear model for all of those proteins. Not too bad. So it took 5 seconds to fit all of those linear models. This is already a subset of a larger data set, I believe. So if we were fitting it on the full data set, that could take quite a bit longer. In this case, it didn't take too long, but we'll see if we can improve it by using parallelization. And so if I look at we're doing MLApply on all of these subsets of the data set, where each subset corresponds to the data for just one particular protein, and we're calling LMFit to fit a linear model to that subset of the data for each protein. So we're getting one linear model for each protein and saving it back to a new column in our nested data frame. So if I look at look at a tidy version of the first model, it's still showing it up there, but if I show it down here, so we can see it has all of the estimates for each different run and so forth. But we're more concerned with just how fast we can make it right now. for the sake of example. So a really straightforward way to do parallelization is using just MLApply from the Parallel package. So this is just a multi-core version of MLApply. So MLApply it was originally written in that multi-core package that the Parallel package integrates. And so MLApply only actually works on Unix systems, so Mac and Linux primarily. MLApply will not work on Windows. I'm not sure if it'll just give you an error or if it'll actually just go and do lapply. I'm not sure what it'll do, but so MLApply will only work on Unix systems. But just so it's one of the easiest ways, so let's just try this first. So by running the linear model fitting on all of these proteins in parallel, we shaved off about a second from the runtime. So what MLApply is doing is for each element of this list column in this data frame. So basically, for each subset of the data set, it's going to fit a model for each of those subsets in parallel. Now, I believe it'll default to just using 4 cores. So it'll just create 4 additional R processes and recycle them as necessary as things complete. And we can see that in this case, it only saves about a second of time because in the original running it sequentially only took about 5 seconds. So there's going to be a certain amount of overhead that it takes to actually create those additional R sessions, send the subsets of data to those R sessions, and then get the data back after the results are returned from each of the parallel R sessions. So in this case, we don't see a significant speed up from parallelization, but if this function ran a lot longer, if we had a lot more proteins, or if we had a lot more, after the data set was just a lot larger in general, we might see a more significant speed improvement. But this is pretty good for the sake of example. So because a drawback to MLApply is that it only works on Unix, we're going to use some of the other functions in the Parallel package that can be used on all operating systems. And so these are functions that originally come from that package Snow, simple network of workstations. So they work by spawning additional R processes that you can then control. You can send data to them and so forth. And all of that data is transferred via sockets or R connections. So what we do to create a cluster is we call this function makePsoc_cluster. And then we give it the number of workers. And so we're just going to use the number of cores for that is detected for our machine, which is 4. And so we're just going to make a cluster with a local cluster anyway with 4 workers. You could also, if you were on a network and there were other machines connected to this one with different names, you could actually put the names of those other computers on the network here instead. So when I give it just a number, that assumes it's going to create all of those processes locally, but I could also give it names of other computers on the network. And then it would create the additional R processes on those other machines. So here you can already see that it takes a certain amount of additional overhead to just create the cluster and start those other R processes, which MLApply does automatically, but in this case we do it manually. And so with these other parallel functions, there's a family of parallel versions of several familiar functions from R, such as lapply. So what I'm going to be using here is a parallel version of lapply, basically. Here you can see that there are a number of these for controlling these clusters. So you have cluster call, which just executes the function call on a cluster. Cluster apply is slightly confusingly not actually a cluster version of apply. It actually just takes a function and applies and executes it on each worker in the cluster. And then cluster export will be important later. We'll talk more about that. But cluster export is how you can manually send data to the other R workers, the other R processes. The important ones we'll be looking at right now are these par functions. Primarily Parallelization is what I'll be using here, which is just a parallel version of MLApply. And there are other versions of it. You have like par_sapply for a parallel version of sapply, and then par_apply, par_rapply, and par_capply. So this is just a parallel version of apply, and these two are specifically parallel versions of apply, specifically for rows and for columns. By making one specifically for rows and columns, they can do a little more optimization than just the general version of apply, which has to work for whatever type of array you give to it. There are also in case you have a function that might take significantly longer to run on some machines than others, like either say either one of the machines on your network is much slower than another one, or you know that some subsets of your data set are much larger than others. Say I got a lot more information for one protein than another protein. Then there are also these load balancing ones, and you can use those if you know that some of those processes might take a lot longer to execute than others, and R will try to automatically balance the load of those. But for our case, I'm just going to use the regular parallelization. Okay, so make sure my cluster is still there. Yep. So now I'm just going to do parallelization. I have to give it the cluster that we created. Then I give it the list of data sets, and then the function to apply to each of those subsets. So I can just run that. And that time you can see also that the amount of time it took that to execute was only 3 seconds. And that's probably mostly because we set up the cluster beforehand, whereas when we ran MLApply, that does all of the forking and stuff for us, whereas we took care of some of the overhead of creating the cluster beforehand. And we can take a look at the results. And we can see that the results are just the same as we would have gotten, or as we did get when we just ran all of that on the same host R process. But we were able to shave off 2 seconds of the analysis, which is pretty good. For that's like 2/5 of the full of the runtime, which would matter a lot longer if it was 3 hours instead of 3 hours instead of 5 hours. So that's just a really quick introduction to parallel computing in R using this parallel package. So now I'm gonna revisit this a little bit more later when we talk about scalability for memory and show how to use these with some packages for working with large data sets in R. So I'll come back to this in a little bit and talk a little bit more about things like cluster export. But are there any questions right now about this parallel package so far? Yes.
So when you have 4 cores that you detected, can you just restrict it to run it on 2 cores and use that?
Sure. Yeah. Then I would just when I make the cluster here, I would just give it 2 instead of 4. Mm-hmm.
There's another package called BioC Parallel. So have you used that?
What was it called?
BioC Parallel. I think it's a bioconductor.
Oh yeah. So bioconductor also has their own versions of all of these. So there's and I'm not entirely sure if they're actually their own versions or if they just wrote S4 methods for all of these. But yeah, there's bioconductor specific versions of all of these as well. And I think one of the I'm not sure if they actually have custom coding there, or I know that they turned all of these into S4 generic functions as well. So you could write these as functions for your particular data set or something like that. Yes. So this makes PSOC cluster and stuff. That'll work fine on Windows. Oh yeah, probably yes. Yeah. So that's pretty cool. But suppose you were writing your own package, and you had to decide at some point whether you wrote a function using MLApply or Parallelization. Well, if you wrote it using Parallelization, then at some point you would either have to create a cluster in your package, and then you'd have to do something like decide for the user how many cores they want to use, which the user might not necessarily agree with. So maybe you could take the number of cores as an argument to your function. So then you could ask the user how many cores they want to use or whether they want to execute it in parallel. But then you have to write like an if-else statement, and if they want to do this, run this in parallel, then you use Parallelization. If they don't, then you just use MLApply. So it can create a little bit of extra complications when you want to use these in a package, which may be fine, but there's also other tools so that you can avoid that extra headache if you want to. So one of the ways that you can do that is with this package called for-each. For-each is actually just at its heart, for-each isn't actually a package for parallelization at all. It's just a package that basically implements a kind of a cross between for loops and MLApply. So for-each actually basically just implements this language object called for-each, which works a lot like MLApply. So basically, if I do for-each and then give it some kind of list or something, it'll just apply whatever block of code I give it to all elements of that list. And there's a bunch of other cool things that work with for-each. There's a package called iterators that's associated with for-each, which if you come from a C++ background or something, you're probably familiar with iterators. So there's all these other kinds of cool ways of interacting with data that is associated with for-each, but I'm primarily going to be talking about how to use it for parallelization. So all you need to know right now is basically, here what I'm doing is, this is a lot like an MLApply, where instead of doing MLApply to this data set and then calling the function, I'm just doing for-each to this data set, and then for each element of this data set, which we know is a subset of data, I'm going to do lmfit data. And you can see that the for-each authors are using their own infix function do in order to accomplish some of this. So I could actually have instead of just this, I could also have a whole block of code after that for-each do as well, instead of just a single function. But so now, let's just try this using for-each after we install it. Okay. So first, we're just gonna use it just using normal for-each, and this is basically just gonna execute like I said, like a cross between a for loop and MLApply. So this is just gonna run sequentially on one R process right now. So again, that takes about 5 seconds, just like MLApply. So to run it in parallel, we only need to make a small change. We just change the do to do par. So I actually lied. That doesn't change it to do it in parallel. It changes it to optionally do it in parallel. So when you change that to do par, it'll run it in parallel if you have some kind of registered parallel backend, or it'll just fall back to running it sequentially if you don't. So by using this for-each and then do par, I can write the same code and then leave it up to the user whether they want to do this registering of a parallel backend or not, which I'll show you how to do in just a moment. And we can see, so in this case, it took basically the same amount of time, because I'm again just doing it sequentially when I do it with a do par without a registered parallel backend. So I'm probably going to have to install this. So there's a collection of several packages that follow this do blank naming scheme that are all associated with this for each. There's do parallel. There used to be a do snow back when snow was separate from parallel, and there's also several different versions for various other frameworks for parallel programming in R. I don't actually know all of them, but if you, but yeah, so there's several of these do something packages for registering different kinds of parallel backends in R. I'm just going to do the simplest one, which is just do parallel, which uses the parallel package. But if you're familiar with other kinds of paradigms for parallel programming, there are also other versions of this that can register different backends. There's probably ones for like Hadoop and so forth. But then you have to go through the effort of actually setting all of that up, whereas parallel we get basically for free. So these packages all have a register do something function. In this case, it's register do parallel. And so I do this just like I did earlier when I made the cluster. I do register do parallel and then give it the number of workers I want. I'm just going to use the detect cores again as a default. And now, when I do the same for each do par, it executes in half the time, because this time it actually ran in parallel because I had this parallel backend registered. And I can see that the output is just the same as before. And this time it ran in parallel like Parallelization, but using the same code for both parallel and sequentially. So you could use, so this is an example of code that you can include in a package, and it'll run just fine for all of your users, whether or not they have a parallel backend registered. And if they want to run the code in parallel, then they can register a backend, and it'll automatically run in parallel. So that's all for this quick introduction to parallel programming in R. Are there any questions about that before I move on to memory and large data sets? Okay, so let's move on to talking about large data sets in R. So one of the common problems in R is that it typically requires that you load the full data set into memory before you can do anything to it. And if you have a computer that doesn't have a whole lot of memory, that can be a challenge. Or if your data set just happens to be really, really big, and you don't, then that can also be a challenge, even if you have a lot of memory. But so there are a growing number of packages on both CRAN and Bioconductor that are dedicated to working with data sets that are too large to be worked with in R in a typical way. A few of these are called BigMemory on CRAN and FF on CRAN, and I'll also talk a little bit about Matter, which is my own package on Bioconductor. So BigMemory on CRAN supports two different ways of working with really large data sets. The first one is it uses shared memory from the Boost implementation. If you're familiar with C++, you probably know Boost. If not, don't worry about it. But basically, it uses this Boost implementation of shared memory to store matrices outside of R's normal managed memory. And it stores these matrices in shared memory so that they can be shared between different R sessions. So a common problem if you're trying to do this kind of making a cluster and then sending data to it and running it is if your data set's really, really large, then your first problem is just loading it into your host R session. Your next problem is actually splitting up that data and sending it to all of your other R sessions, because all of a sudden you're using like 2 or 3 times as much memory as it took to just load the data set originally. So if your data set's really large, that's going to be a big challenge. So the nice thing about BigMemory is, since it uses this shared memory strategy, you can actually share the exact same data set between different R sessions without copying it, or also just within the same R session without copying it. It also supports file-backed matrices. So its default is to create these matrices in shared memory, but it also has another mode for file-backed matrices where it creates the matrix on disk and then uses memory mapping to map that file into memory using using memory map mmap on Linux operating systems. And I forget the name of the Windows function for that, but using the Windows equivalent on Windows. It also has kind of a family of these big packages. So BigMemory is the main one that implements these matrices. There's also BigAlgebra, which implements like linear algebra for these big matrices, and BigAnalytics, which implements things like linear modeling for these big memory matrices. There's another package called FF on CRAN, and so this one, FF, just uses flat files for data storage. So basically, all of the any vector or matrix in FF is just going to be a file on disk, and it's just going to be just a flat file without any special things attached to it. And so whenever you read from an FF vector or read from an FF matrix, you're actually reading that from disk, which for smaller things will be a lot slower than doing it in memory, but for really large things can be a lot faster, because then if your data set is too large for memory, then you're going to be swapping to disk a lot anyway, so just doing it in a more efficient way with FF will likely be a lot faster. You have a lot more storage space than you do memory, so if you use that storage space in an intelligent way with large data sets, it can be a good resource. So FF is on CRAN for using flat files. There's a number of other packages that extend FF, which are not written by the original authors of FF, but nonetheless are really useful. So there's a package called FFBase, which adds other things to FF vectors, FF matrices, and FF data frames, and so forth. So it adds things like arithmetic and to FF objects and so forth. And lastly, Matter is a new package on bioconductor. So it's really similar to FF in that it also uses on-disk files for its data storage. The main difference with FF is between Matter and FF is that FF just throws your data into a flat file on your disk, and you can't. There's no real customization in how that data is stored. And if you already have some existing data file, you can't really customize FF to be able to use that existing data file. Whereas with Matter, the main difference with FF is that it tries to support custom data formats. So if you are coming from, so for example, you have some kind of new mass spectrometry instrument that you got from a vendor, and it creates these certain kinds of files, and you want some way of reading those files, then depending on whether the vendor actually made that file format open source or not, the idea is that Matter would be able to read those files if you just tell it where the things are stored in that file. So the main motivation behind writing Matter was to create an R package that could natively read IMZML files for mass spectrometry imaging without having to actually convert it to a different file format. Yes?
So would it be more useful for other large file state the tag separated file by not needing to load it into R first and then convert it out with FF-based?
So one thing is all of these are working with binary data, so not text files. BigMemory and FF will have functions for reading text files and converting them to their binary format. but none of these will work natively with a text file. So at some point, if it's in a CSV or tab delimited file, at some point with any of these, it's going to have to be converted to some kind of binary format.
Is there a lot more conversion overhead for FF and BigMemory versus Matter?
Let's see.
You know what I mean?
Yeah. Well, right now, Matter doesn't have its own function for working with text files, since it was primarily written with the idea that you already have some kind of binary file that you want to work with. Whereas BigMemory and FF are kind of assuming that you have some huge CSV file or some huge tab delimited file, and you want to convert it into a binary format that they can work with. So if you're converting something that's well, another thing is I guess it depends is whether your text file is whether you want it to actually end up as numbers or not. Because so if it's numbers in this text file, then that's what BigMemory and FF will do. They'll read the numbers in the text file and convert them to their binary representation. If you're actually working with strings, say like in a genomics experiment or something where you have like ATCG and so forth, then BigMemory and FF won't work with those because they don't work with strings or character vectors or anything like that. FF will kind of work with strings a little bit in that it supports factors, but the factors are actually integers with labels. So if you're actually primarily interested in strings, then BigMemory and FF will not work. Matter won't work yet, but it's close. That's one of the things I'm working on right now is actually supporting working with text files as strings without loading them into memory in Matter. So that's something that I'm working on right now with Matter, but it's not quite there yet. Okay, so let's take a look at how to work with each of these. So suppose we want to run linear regression on a quote-unquote large data set. This is actually a pretty small data set just because I want to be able to run these without waiting for a long time. So here I'm just generating a data set with 10 columns, adding some random noise to it, and that's all that's really important about it. So I just created a data set with 9 columns and a certain number of coefficients. I created a y response vector from those coefficients, but in addition to some random noise. So I want to try to do some linear regression on this data set. Also note that so earlier we learned that using primitive functions doesn't increase the refs count for an object. As it so happens, the normal assignment method for data frames is not a primitive. However, the assignment for lists is a primitive. So in this case, I'm saving some memory by I'm creating the data as a list first. I'm assigning all of the data columns as elements of this list, and then I'm coercing it to a data frame. As it turns out, this is more efficient than if I tried to create it as a data frame in the first place, because the assignment operator for data frames isn't a primitive function. So here I can do it faster by using the list assignment operator. Okay, so like I said, this is still a relatively small data set. It's only 80 megabytes. The example data set we were looking at earlier was only 5 megabytes, so it's still at least a little bit bigger than that. But nonetheless, well, we'll work with this one. So here, just to save time later on, I'm creating a formula for the linear model and saving it now, so I don't have to retype the whole formula each time. So here I just want to model y as the response for all of these 9 x variables. I'm also going to go ahead and recreate those memory overhead functions that I created earlier today, because I want to see how much memory it actually takes to fit this linear model for this still relatively small 80 megabyte data set. So it takes about 180 megabytes just to fit the linear model for this 80 megabyte data set. And so you can imagine so that's more than twice the size of the data set itself. So you can imagine if you had a data set that was 5 gigabytes, it would take more than 10 gigabytes to actually fit the model for it. So that's a reason why it's a good idea to know that these other ways of working with the data exist. So first I'm actually going to just do bootstrapping. So I'm not actually going to go through and create confidence intervals from this, but suppose I wanted to do some kind of bootstrap confidence interval where I take random subsets of the data, fit linear models to those, and get all the coefficients from all of these bootstrap samples, and then create confidence intervals from them. So here I'm going to fit a bunch of a bunch of models doing this bootstrapping from these bootstrap samples in parallel. And to do that, I'm going to load parallel. I'm going to create a cluster. I'm going to create a bunch of seeds for the random number generator on each of the for each of the bootstrap samples. And so cluster export is how I export the data set from this host process to the other processes. And remember, right now I'm still just using regular R data frames. So this is before I actually show you how to do this with BigMemory, FF, and Matter. So now I can do Parallelization on the seeds for these. On each worker, I'm going to set the seeds so that each one gets a different random sample. I'm going to take a sample subset, random subset of the data set, and I'm going to fit the model to that subset. So that doesn't take too long. And in this case, all of this example is still relatively small enough that parallelization isn't actually really going to do much for us. This is more of a proof of concept, so you can see how to work with these types of data sets if you had a much larger data set. So now I can show you how to do the exact same thing, but using BigMemory and the big matrix class from BigMemory. Of course. Okay. So with BigMemory, it's all based around this class BigMatrix, which you can see here. And so the BigMatrix is just the R front end for this implementation that BigMemory has in C++, where they work on these shared memory matrices. But all you need to know from the perspective of an R user is that you can just type big matrix instead of typing regular matrix, and then access it like you would a normal R matrix. So in this case, I'm just doing big matrix, giving it the same number of rows, number of columns as the original data set. The DIN names I'm changing slightly. I'm giving it the same column names, but I don't need to bother giving it row names since they're meaningless in this case. Then I'm just going to go through the columns and assign them. So you can see when I just type data.bm, it's just a pointer to some object in C++, some C++ object. So BigMemory uses an external pointer to point to its own C++ class and has all of its own special functions for managing that. But all we need to know as an R user is that you can still do things like this. And it just works like a normal matrix for the most part, as far as we're concerned. So now how to actually use that. with the cluster is, so because BigMemory uses these external pointers, you can't actually directly just export the big matrix as is to the other R sessions. Because it's using this external pointer and R's regular, the way R serializes data sets, it doesn't know what to actually do with an external pointer. So what you do instead is you call this describe method on the BigMemory data set, and it'll create its own descriptor that you can then save. Then you can export this descriptor to the clusters. Then on each of the workers, I do the same thing, setting the seed for the random number generator. I make sure BigMemory is loaded. And then I call this attach big matrix function. And that it uses the descriptor to find the same external pointer and then attaches the exact same big memory matrix in the other R session. So it's using the exact same data pointing at the exact same shared memory. So nothing gets duplicated in this version. And then because LM expects a data frame, I convert it to a data frame too. I'm not sure if this will actually work. When I tried it earlier, it was broken. Okay, cool, it worked. Yeah, for some reason for me earlier, the shared memory version was broken for me, but here it works just fine. Yes. I'm not sure what was going on with mine. So the other way that you can work with big memory matrices is using the file-backed version. So this creates a file version of your data rather than storing it in shared memory. So here I'm just going to create a file where I want it to point to. Then I have to give it the path to where I want the data stored, the name of the file, and a name of the descriptor file. So I'm just going to put those in a temporary location. Assign to it just like usual. And still, you can see that it's still just a pointer to some C++ class that we don't need to know about. And it's still, you can still access it just like a normal ordinary matrix. And in this case, the actual size of the data set itself in memory is really tiny because it's actually this file on the disk instead. So now I can do literally the exact same thing as I would before, using the describe and then attach big matrix. And that runs pretty quickly again. So that's just a quick intro to the BigMemory package. And now I'll show you FF. So the nice thing about all of these packages is I can actually work off the exact same file for the rest of these examples. Because both FF and Matter can work with basic flat files like a file-backed big matrix creates. So when I do library, I'm actually just going to create an FF object from the same file that I created earlier. So with FF, it's actually it has a whole ton of different options for a lot of control over the data set. A lot of these are actually just because you can create a bunch of different, whether you can create like an array or a vector or a matrix from the same constructor, so it has the parameters for all of them. But the most important things right now are just the V mode, which is basically the type in C or C++, so like an integer, double, and so forth. So what I created before was a double matrix, so I'm going to do vmode double, give it the same dim and dim names as the file-backed big matrix, and then just give it the same file as the file-backed big matrix created. And so here, I can see again, I'm actually just accessing the same file that file-backed big matrix created. And again, I can just access it like an ordinary matrix like I would in R, although in this case Something's a little off with the head, but with the head function for it, but everything else works just normally. And again, the actual metadata that's actually loaded into memory is really small compared to the actual size of the matrix on disk. So with the case of FF, it's not using the external pointers that BigMemory was, so I can just export the object itself, and it gets serialized to the other R sessions perfectly fine. So I can just export the data.ff FF matrix, and it'll go to those other R sessions just fine when I run it in parallel. And lastly, matter, like FF, it'll work with the same kinds of files. So here, I'm just going to load matter. I'm just going to give it for the file path the same file name, the same number of rows, same number of columns, same dim name, and so forth. Again, the actual metadata is much smaller than the actual data set on disk, but we can still access the data set just like we would an ordinary R matrix. And we can run it over the cluster the same way. I think this one's going to take a little bit longer, and I'm not sure why, honestly. I think it's actually mostly in the loading. The package takes a little bit longer. But anyway, so those are just a few different packages that can be used for working with larger than memory datasets, or just generally really big datasets that can be difficult to work with in R otherwise. Are there any questions about any of those before I move on to writing C and C++ code for R? Yes?
Have you encountered when in R whether there is a way to do distributed computing, like if data set is stored elsewhere and then you get small chunks of it and then divide and recombine?
Okay, yeah, so there are also a lot of other strategies for working with large data sets in R, especially in other languages. Right now, mostly what I was talking about was approaches that you can just use solely from within R without calling any other languages, and also just that you can run on a single machine. But there are also other packages and approaches that can work better when you want to run something, say, on the cloud, or when you do have a network of other machines. And some of those use other infrastructure like Spark or Hadoop and so forth. For example, there's a package called Repay, which implements basically Hadoop for R. Of course, then you have to make sure you have Hadoop and Java installed, and you have to be a little bit familiar with Hadoop and how to do this divide and recombine thing. So there are a lot of other packages that will do these sorts of things for R. I think there's actually several that implement Hadoop, and JJ talked about a Sparkly R or Sparky R, I forget, earlier about working with Apache Spark from R, and so there are quite a number of these packages, but I'm not going to talk about the rest of them right now, but there's plenty of information out there for those. And there's definitely quite a number on working with things like Hadoop and so forth. Any other questions on the large data sets and parallel computing in R? Okay, then let's move on quickly to the how to write C and C++ code in R. So typically when you're writing something in R and it's taking too long, lots of times the first thing that you should really do is just figure out how to write it faster within R itself, because there's usually a better way to write it in R itself. But sometimes you'll have functions that you can only do so much in terms of improving the speed within R, and to get much more performance out of them, you really do need to go down into C or C++. And usually one of the main candidates for these are things that do involve a lot of for looping and can't really be vectorized or further improved. And I mentioned earlier, during the earlier session, that for loops in R aren't necessarily that slow. But sometimes if you do have a bunch of nested for loops, then they do run a lot more slowly than C or C++. And the reason for that in R is because each iteration of the for loop, R has to completely reinterpret the code in that code block of the for loop. Whereas in C or C++, all of that code is compiled beforehand, and so you don't have much additional overhead for just each additional iteration in C or C++. Whereas within R, just the fact that you have R has to reinterpret the function calls each time at each of those iterations of the for loop adds a lot of overhead. Jan talked earlier yesterday about how everything in R is actually a function call. So just the parentheses operators in R, just the parentheses is actually a function call in R. So just when you add a bunch of extra parentheses around something in the body of a for loop, that'll make it take potentially a lot longer. In practice, not that much longer, but if you have a lot of iterations of a for loop or something like that, it'll add up over time. So usually when you have a bunch of nested for loops or something like that and you can't easily vectorize them, that's a good candidate for rewriting that function in C or C++. So there are 3 common ways to write C or C++ code for R. I'm going to talk about all 3 of them. There's the .c framework, the .call framework, and lastly there's the RCPP package, which is probably the easiest and the one that most of you should use, because the other ones can be difficult and confusing, as JJ pointed out. But I'm going to show them to you nonetheless. So first, to explore how to write C and C++ code for R, we need a good candidate for a function to rewrite in C or C++. And I'm going to do that using a function for finding the median. Let's ignore for a moment that the fact that R already has a function for finding medians and pretend that that function doesn't exist. So I have this function for finding the median of some vector. As you can see, it's a nested for loop. So in the outer loop, I just loop through all of the numbers in a vector. And in the inner loop, for each element of that vector, I loop through the whole vector again and count the number of elements in that vector that are greater than and less than that number. And then I just return the element for which the number of elements greater than and less than it are either equal or only different by 1. So later on, you can take a moment and convince yourself that this actually works. But I'll test it right now. Versus okay, cool. Looks like I have a working median function. And so the first thing that we want to do is actually just quickly benchmark this function and see just how slow is it actually. So as we can see right now, it is significantly slower than R's version of median, which in fact at some point executes its own C code, whereas our version of median just runs purely in R using nested for loops, which is not the best thing to do in R. So say we want to rewrite this function using some kind of C code. So the first, and I say simple, but compared to RCPP, it's not necessarily simple, but it's simpler than the .call framework. So the .c framework is basically the first version of making it the first version of allowing users to execute C code from R. So it's a bit older and a lot simpler and less powerful than the later versions. It only allows basic C types. You can't actually work with more complex R objects using .c, and you have to return everything using out parameters rather than actually returning values. And also, when you call it, all of your arguments will be duplicated. They'll be copied. So it's not the most efficient if you're doing it with large objects. So typically, if you're using .c at all, it should be with smaller utility functions that aren't going to need to do a whole lot of data manipulation and don't really care if their arguments get duplicated. So this is just what it looks like to write a C function using the .call framework. So all of the arguments are pointers to basic C types. I have since they're all just basic C types, I also need to make sure, in addition to x, which is going to be the vector that I want to loop over, I also have to make sure to give it n as the length of the vector and an out parameter so that I can actually return the result of the analysis. So with both the .c and .call, I need to include this r.h header, and since I'm using the absolute value function from the standard library, I'm also including the C standard library, or standard lib.h here. So here I'm basically just doing the same thing that I was before, except with C pointers instead of in R. And again, you can look at this later if you feel like it and convince yourself that it works. But for now, the main things that you just need to notice are that the first argument is this pointer to a vector of doubles, which is the argument that I actually want to pass it. All of the arguments have to be pointers, so I can't actually just pass the length as a regular int. It has to be a pointer. And then I have to have this out parameter for the value that I actually want to return. And so a little bit of a weird thing about this .c framework is, so what it returns is actually just a list of the arguments that it was given to it and reflecting any changes you made to them within the function, which is why I have to use these out parameters. So I saved this function. I made it available to you in this source directory under the folder for this particular session. I called it C_median, and I can compile it using the rcommand shlib command line command that JJ talked about earlier. So I can just run that, and it'll compile it. And now it's a shared library, which I have to load using this dyne.load function. And then I can call .c. So the first thing to give to .c is just the name of the C function. Then I want to make sure that x is actually a double, give it the length of x. And finally, I just need to create some additional argument that it can actually use as the out parameter. And then because it returns, what it returns is actually a list of all of its own arguments, I'm just taking the third element of that list for the actual output. So that's a real quick intro to the .c framework. Let's move on to .call and scare you a little bit more. So the .call framework is a bit more difficult to use because it requires knowledge of various internal R macros and functions. But the good side of it is that it allows you to work with any R object, and you can also return R objects rather than using these clunky out parameters that the .c framework requires. You also get some more control over allocation of memory and things like that, but that comes with its own dragons and things to worry about and be afraid of. So you can see the code for this .call version is quite a bit more complicated already. So everything in this .call framework, everything that's passed to it from R as an R object is an SEXP object, is an SEXP type. So that stands just for S expression. So everything in R is a SEXP, is a SEXP object, and you have to kind of know what to do with those. But it also just means that I can just pass it X directly. Here I can get the length of X using this length macro, and I can create create a new object to return rather than relying on out parameters. So I can do that by declaring a new SEXP variable, and then when I actually allocate it, I can allocate it using this new numeric macro. But when I do that, I also have to call it with these protect macros, which protects that memory from R's garbage collector. Otherwise, what you just allocated might suddenly disappear if R's garbage collector runs. So you have to, if you create a new object like that, you have to protect it. And then at the end, before you return that object, you have to unprotect it. And you can see that, so the SEXP objects are these structs actually that different macros that you can apply different macros to. To actually get the data out of them, for doubles you need to call real on it, and that'll give you a pointer to the head of the actual data. If it were an integer vector, you would call integer to the head of the actual data. And if you are more curious about all of these different internal R functions and macros, they're all documented in this extensive R internals macro that will tell you more than you ever needed to know about how R is implemented. And if you're programming using the .call framework, you will eventually need to learn. But fortunately for most of you, you can get away with using RCPP, which will clear up a lot of those headaches. And also, if you do happen to code using this .call framework, it's a good idea to take a look at the actual R source code, especially the headers rdefines.h and rinternals.h, which has the lists of all of these different macros like new, numeric, length, and so forth, so that you know that they exist. But a lot of writing code for this .call framework is basically digging around in these R source code headers and figuring out what macro you need to use to do something. And as I mentioned, whenever you allocate a new object, you need to make sure to protect it and then unprotect it later on. So I can compile this again from R, or from the command line using just rcommand shlib. I have it saved as call_median.c. I can compile that. I'll load the shared library for that. And here I can just pass it x, or in this case, x is actually an integer, and I assumed it was a double in my code, so I'm actually going to coerce it to a double here. But it just returns the result, since I can actually just return the value instead of having to use these out parameters. So that's .call real quickly. And to wrap things up, let's take a look at RCPP, which is probably the easiest one to use and what most people generally should be using, unless you're doing weird advanced stuff like I sometimes do. So RCPP is generally the easiest to use. It allows you to use most any R object. Most R objects are implemented in RCPP, or at least wrappers around them are. You can return R objects, and you also get all of the power of C++ and the C++ standard template library, which you can also do in .call. You can also use. You don't actually have to write purely C code for .c or .call. Excuse me. But you can mix C++ code with .call C code, but anything that you eventually call from R for those, you have to write extern C around. If you don't know what that means, you probably don't need to worry about it. But so for RCPP, you can see that this already looks a lot more readable and a lot more familiar if you're at all familiar with R code. So to use RCPP, you just need to include the RCPP header. If you don't want to include RCPP : before all of your calls to RCPP functions, you add using namespace RCPP. And then also you need to add this comment directive, RCPP export, if you actually want to be able to call this function from R. So that'll be ignored by most things, but it tells RCPP that you want to use this function in R. And then you can see that it has these nice C++ wrappers around lots of the basic R types. So instead of having to deal with an SEXP object, I can just deal with this numeric vector, which strongly resembles a C++ standard vector, if you've ever worked with those. So I can just, for example, to get the length of it, I can just call x.size on it. I can just assign directly into it rather than having to call real on it to get a pointer to the head of its data and so forth. And here you can also notice that I can actually, to return it, I can just actually declare a double and just return the double. However, if I wanted to return a vector, I could return a numeric, create a new numeric vector instead. But RCPP is intelligent enough to see that when I want to return a double here, it'll just automatically convert it to a length 1 numeric vector in R and give me the correct data type in R. So with RCPP, I can compile that using source CPP. And then I can, so I called the function RCPP underscore median, and I can actually just call that function directly because RCPP creates an R function with the same name as that C++ function that I wrote. So now let's go ahead and create wrapper functions for the .c and .call ones as well, and compare the performance of all of these. So we can see that all of the C and C++ versions are much faster than just the straight up R version. And in this case, the RCPP version is also quite a bit faster than the C and .call version. A lot of that is probably just due to variance and the fact that RCPP takes care of a little bit of additional when you have a bunch of C++ or C functions that you want to call from R, it'll take a little bit of extra overhead to actually find the correct C and C++ function, and I think RCPP does a little bit of extra optimization for us than we did just now. But also the reason that it's faster than R's own median function is that we played a little bit fast and loose in terms of checking for errors in our versions. So we didn't handle NAs and missing values at all. So if you're interested in some homework, you can edit that code so you can actually handle, check for errors, handle missing values, and that sort of thing. But that's the main reason the RCPP version is faster than the base R versions here, is they just do a lot of extra error checking that we didn't worry about. Okay, so yeah, so probably RCPP is the framework that you would want to use if you're actually writing code to analyze data in C++ and R, because it's just a lot easier to use in most cases. So that's all the material that I have prepared for this. Are there any questions about C, C++, any of the .c, .call, RCPP frameworks? Yes. Yeah, I don't know. I can try to help you later if you want, but I'm not sure. Sorry. All right. So thanks. So after this session, we actually have a game to wrap up the week with. That's also a review. But so I'll give you a short break before we do that. But if you want to start, take a break and get into groups or something, you have a chance to compete against each other in Jeopardy.